Another reason we need to understand centroids is to be able to calculate distributed load resultants and to understand fluid pressure. Let's review what we already know. We've learned about how to deal with distributed loads like this, and we know that the area will be the resultant, and the resultant will be at the centroid of the area. And these types of loads are in force per distance, in this case pounds per foot. They might be in newtons per meter. The total load is the area under the triangle, and the total load is located at the centroid of the area, 1/3 of the way over of that 9 feet. However, loads in real life are not like this. You do not find loads in pounds per foot in nature. What you usually have is force per area, or pounds per square foot, pounds per square inch, that's a PSI, Newton per square meter, which is a Pascal. We often call this force per area pressure. So here is what we have been doing using these pounds per foot in these 2D problems, but real life is 3D. And so instead of pounds per foot, you're going to get this pressure P per square foot, or per this area right here. So you'll have a certain amount of force distributed over that area. Let's compare these two things. In the one we had been doing on the beams, the load is in force per distance, for example, pounds per foot, and the total load is the area of that triangle, and the total load is located at the centroid of the area. In these pressure loads, these real-life pounds per square foot, the load is in force per area, pounds per square foot. The total load will be the volume under this surface, and the total load is located at the centroid of the volume. And we've learned how to calculate centroids. That's what we've been doing. When we compare the calculations of these two, in the 2D problem right up here, we have the load is in force per distance, the total load is the area, and the total load is located at the centroid of the area. The parallel to that in the 3D is that the load is the volume. Okay? If you think of P as the height, and over dA, that's the same as the integral of dV, because the height times dA is the differential volume. And to get the weighted x with respect to the pressure, you do x pressure dA, or x dV, divided by the total pressure dA, or dV. And see how that's just the centroid we've been doing, integral x dV over dV, and integral y dV over integral dV. Often when we do these pressure calculations over area, the pressure is constant. It might be something like 40 pounds per square foot. That would be roughly how much people weigh in a room. Or we would say it equals 50 pounds per square foot. That's how much a 4-inch thick slab of concrete would weigh per square foot. You can look these things up, and they're constant, so then these integrals are very easy. It's just the integral of a constant over dA. So the constant times the area will be the volume. However, there is one application where the pressure is not constant, and it's fluid pressure. We do this a lot in civil engineering and mechanical engineering. You'll do this in Mechanics of Materials, ES 2410, but it'll be good to review it now. So here are 5 things you need to know about fluid pressure. 1, pressure increases with depth linearly. 2, the pressure is the depth times the density of the fluid. 3, pressure always acts perpendicular to surfaces. 4, the fluid we most likely will deal with is water, and water's density or unit weight is 62.0 4 pounds per cubic foot, and its density or mass per unit volume in metric is 1,000 kilograms per cubic meter.